Let's kick things right off. Welcome back, everyone. We are jumping straight into week 3, day 15 of our distributed systems curriculum. Today's explainer focuses entirely on, literally, the absolute backbone of scalable architecture, message queues. Look, if you want to understand how modern apps handle massive traffic without just completely collapsing, well, you're in exactly the right place. Okay, let's quickly hit today's agenda. We're covering 1. Queues versus synchronous requests. 2. We'll meet producers and consumers. 3. RabbitMQ and Kafka concepts. 4. Retries and dead letter queues. And 5. Your practice build. Let's dive right into section 1. Queues versus synchronous requests. To start, we really need to address the ultimate bottleneck problem in system design. Let's contrast two very different approaches using an upcoming email processing project as our analogy. If you build a system using a synchronous request, your app is blocking and waiting for a task to finish. Imagine you want to send a user a welcome email. In a sync model, your main application talks to the email server and simply stops. It flat out refuses to do any other work until it gets a confirmed delivery receipt. It's basically like standing at the post office counter and refusing to step aside until your letter is physically handed to the recipient. It halts everything. Versus a queue. Here, you just drop off the message and move on asynchronously. You check the letter in a mailbox and immediately get back to your day. This distinction, it's the absolute secret sauce to high-performing systems. Section 2. Meet producers and consumers. Now that we get why queues are so crucial for keeping things moving, let's meet the actual actors handling the data. First up, the producer. This is the entity or service that creates and sends messages into the queue. Back to our email analogy, the producer is that specific, fast-moving part of your app, like the user registration service. The second a user clicks register, the producer fires off a message saying, hey, send a welcome email to this address, and drops it right into the queue. And that's it, job done. It produces the intent, completely decoupling itself from the actual execution. On the flip side of the queue, we have the consumer. This is the worker that pulls messages from the queue to process them. This is the hardworking background task of your system. It constantly monitors that queue, picks up the message the producer left behind, and does the heavy lifting, like actually connecting to the SMTP server and sending the email out. By separating the producer from the consumer, neither one waits on the other. You can scale them completely independently. It's honestly brilliant. Moving right along to section 3, RabbitMQ and Kafka concepts. So how do we apply this in the real world? Let's look at the industry heavyweights and their foundational differences. RabbitMQ is your popular, traditional message broker. It excels at complex, specific routing. If you need a strict guarantee that a specific message goes to a specific consumer and is deleted right after processing, RabbitMQ is your go-to. Kafka, on the other hand, is an event streaming platform built for incredibly high-throughput distributed systems. It acts way more like a massive append-only log where messages persist and the consumers actually keep track of their own reading progress. Knowing whether you need the smart, surgical routing of RabbitMQ or the heavy-duty, replayable streaming of Kafka is absolutely crucial for any systems architect. All right, section 4, retries and dead letter queues. Look, in distributed systems, failure isn't an if, it's a when. Let's map out the active timeline of a failure so we don't get blocked by bad messages. Step 1, message processing fails. Maybe our consumer hits a bounced email or a random temporary network glitch. Step 2, the system triggers a retry. We don't just toss the message in the trash right away, we tell the system, hey, try again in a few seconds. But what if it's a permanently invalid email? We can't retry forever, right? That takes us to step 3. The failed message gets routed to a dead letter queue. And what exactly is a dead letter queue? It's a designated holding area for messages that cannot be processed successfully after a set number of retries. Think of it as a quarantine zone. It keeps your main queue flowing completely smoothly, completely bottleneck-free. Meanwhile, your ops team can pop open that dead letter queue, inspect the failed messages, figure out what went wrong, and either fix a bug or manually reprocess them. It is without a doubt the ultimate fail-safe for asynchronous architecture. Finally, section 5. Your practice build. Okay, we've covered the core concepts, the primary tools, and the vital fail-safes. The whole goal of this explainer is to arm you to crush today's practice assignment, building an asynchronous email processing system. You are going to take everything we just talked about, the queues, the producers generating tasks, the consumers executing them, and the safety nets, and turn them into working, functional code. This right here is where the theory hits reality. So, are you ready to build? I'm going to leave you with this thought as you jump into your coding environments. What major bottlenecks in your past projects could have been entirely eliminated if you just used a simple message queue? Seriously, think about it. You now have the blueprint to decouple services, massively speed up response times, and handle network failures with total grace. Go fire up those queues and let's see those background processes in action. Have fun and happy building.